This is the 20th video in a series devoted to introductory proof writing. And today we're going to do proofs that might come from an advanced calculus class or maybe the very beginning of a real analysis class. And I think this is kind of a new thing, introducing these types of proofs into introductory proof writing classes. The standard for a long time was to focus on proofs that came from number theory or other types of discrete math, whereas these come from continuous math. So I think that's a really good idea because it gives you a more holistic view of the types of mathematical proofs that you are going to see in upcoming courses. Okay, so today we're going to be focusing on the precise definition of a limit. So it's possible you saw this in an introductory calculus class, maybe like differential calculus or calculus 1, but not everyone covers this in that sort of class. Okay, so let's suppose that f is a function from a subset x to R, where x is a subset of the real numbers, and a is an element of x, so a is a real number. Then we say that the limit as x approaches a of f of x equals L, and use this standard notation, if the following statement holds. So let's read this and then parse out what it means. So we have, for every epsilon bigger than 0, there is a delta bigger than 0, such that if x minus a is less than delta, then f of x minus L is less than epsilon. So some authors write this as sort of a challenge. So you challenge someone by giving them a very, very small number epsilon, and they stand up to that challenge and give you a number delta, so that as long as x is within delta of a, f of x is within epsilon of L. So in other words, this is kind of saying that if x is very, very close to a, then f of x is very, very close to L, but it's doing it in a more precise way. So here's a picture of what's going on. Let's say this green is the graph of a function, so it's like the graph y equals f of x. And then we have our point down here, a, and then our L here, which will be our eventual limit. So the given epsilon tells you to essentially make this epsilon band around this horizontal line L. So notice up here we have L plus epsilon, and down here we have L minus epsilon. And then this existence of a delta tells us that we can get close enough to A so that the graph is always within this epsilon band for the inputs that are, like I said, close enough to A. So notice that's what we have here detailed. So look at our little rectangle, which is from A minus delta to A plus delta, and then L minus epsilon to L plus epsilon. And our graph is totally within that rectangle. And so that would be like a graphical representation of this happening. So we could squeeze these two epsilon bands together, and that will cause these delta bands to squeeze closer to A. So that's the sequence of events. The epsilons get squeezed first, and they cause the deltas to squeeze. Okay, so we're going to need three standard lemmas in order to look at some of the proofs that we'll look at eventually. And they're all versions of this triangle inequality. And so let's look at the most basic version first. So I'll call this a lemma. It's the triangle inequality. It says if x and y are real numbers, then the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. In the real numbers, this is not so obvious why it's called the triangle inequality, but in R2 it is, because this is the difference between going along two legs of a triangle versus just taking the shortcut. Okay, so let's see how this might work. We'll start with the right-hand side. So we've got absolute value x plus absolute value y, and we will square it. So that'll give us the absolute value of x quantity squared plus 2 times the absolute value of x times the absolute value of y plus the absolute value of y squared. Okay, nice. But now notice that the absolute value of x squared and the absolute value of y squared is the same thing as just x squared and y squared, given that we're in the real numbers here. Also, the absolute value of x times the absolute value of y is bigger than or equal to x times y. So that's how we build in our inequality. This is bigger than or equal to x squared plus 2xy plus y squared. So again, we make the inequality by dropping the absolute values. This to this is equality. This to this is equality, but here to here, these middle two terms are inequality. But now we can factor this. This will be x plus y squared. But squaring something and taking the absolute value and then squaring are the same thing in the real numbers. So this is equal to the absolute value of x plus y squared. But let's notice we've got a positive number squared, a positive number squared. That means we can take the square root and the order remains. So taking the square root, we have the absolute value of x plus y over here, and then bringing down the inequality in the correct direction, we'll have the absolute value of x plus the absolute value of y, but that's where we needed to end. Okay, so now let's look at our two other versions of the triangle inequality. So the next version of the triangle inequality we'll look at is sometimes known as the reverse triangle inequality. And it involves subtraction instead of addition. It says that if we have real numbers x and y, then the absolute value of x minus the absolute value of y is less than or equal to the absolute value of x minus y. So we'll start with our normal triangle inequality, so our initial triangle inequality. And I'm going to rewrite this with u and v. So we have the absolute value of u plus v is less than or equal to absolute value of u plus absolute value of v. And then what we'll do from here is evaluate this for different values of u and v to produce things that look like our goal inequality. Okay, so let's start with u equals x minus y, and then v equals y. Let's note that immediately that tells us that u plus v is equal to x, just by simple calculation. So plugging this into our triangle inequality, which we proved on the previous board, gives us the following inequality. So x plus y is x, like I said, and we have that's less than or equal to the absolute value of x minus y plus the absolute value of y. So we have something like that. Okay, good. Now let's move this around so it starts to look like what we have over here. So moving this absolute value of y to the other side of the inequality gives us absolute value of x minus absolute value of y is less than or equal to absolute value of x minus y. Okay, let's put a box around that because we will hold that for just a bit. Okay, now we'll take our original inequality and evaluate it somewhere else. Well, it's at a pretty similar place. Let's take u to be equal to y minus x, and we'll take v to be equal to x. So immediately we see in this case, u plus v is equal to y. So what does that do for us? So we have u plus v in absolute values on the left-hand side. Like I said, that's y in absolute values. So we have absolute value of y is less than or equal to. So we'll have u, which is absolute value of y minus x, plus v, which was absolute value of x. So something like that. Okay. But now let's move some things around here and see what we get. So here we'll have absolute value of y minus absolute value of x is less than or equal to absolute value of x minus y, where I took the opportunity to change the order of subtraction from y minus x to x minus y, given that I'm inside of absolute values. So that's not really a problem. Now let's put the green and the blue box together and see what we have. So reading this green one off just as is, we won't change that, but we will change this blue box a little bit just to make it work a little bit better with our final goal. Notice that this is equivalent to saying negative absolute value of x minus absolute value of y is less than or equal to absolute value of x minus y. And now let's put a green box around this one because it's playing a similar role to the one above. But notice that these two inequalities are equivalent to the compound inequality that we want. So in other words, these two put together say that we have absolute value of x minus absolute value of y, all in absolute values, is less than or equal to absolute value of x minus y, which is where we wanted to end up with this reverse triangle inequality. Okay, now let's look at another version. Here we've got another version of the triangle inequality, which will follow very, very quickly from the original triangle inequality. So we have absolute value of x minus y is less than or equal to absolute value of x plus absolute value of y. Okay, so let's get going on this. Like I said, this will be very quick. We have absolute value of x minus y is equal to absolute value of x plus negative y. But now we'll apply the normal triangle inequality to that. That will be less than or equal to the absolute value of x plus the absolute value of negative y. But the absolute value of negative y is clearly just the absolute value of y, and that takes us home. Okay, so now let's do some examples of showing limits have certain values using our precise definition. Now we're going to do some examples where we show certain limits have certain values using our precise definition. And this is going to involve a scratch work. So we're going to do scratch work, and then during our actual proof, we'll essentially be writing our scratch work in reverse. So I think this is the standard way to approach this. And this scratch work first method is fairly similar to what you did when you proved a function was surjective. Okay, so let's show that the limit as x goes to 2 of 3x minus 1 equals 5. So that value should be somewhat familiar from a calculus class. Okay, so now let's do our scratch work, which means we're going to start at the end. We will start with this condition right here, f of x minus L is less than epsilon, and we'll work back towards this condition, x minus a is less than delta, and delta should depend on epsilon. Okay, so let's get to it. So we want the absolute value of 3x minus 1 minus 5, like I said, to be less than epsilon. Great. And then just looking ahead, down here at the end, we should have the absolute value of x minus 2 less than something. And that something is exactly what we will call delta. Great. And how do we know it's x minus 2? Well, because we're having x approach 2. And how do we know it's 3x minus 1 minus 5? Because 3x minus 1 is playing the role of f of x and 5 is playing the role of L. So in this case, there's not much to it. This will be quite quick. Let's simplify this inequality right here, or maybe the interior of the absolute value, giving us the absolute value of 3x minus 6 is less than epsilon. But notice that we can factor a 3 out of that, leaving us with 3 times the absolute value of x minus 2 is less than epsilon. So clearly we use the fact there that the absolute value of 3 is 3. And then finally, we can divide 3 on both sides and we'll get epsilon over 3. And so that will be our choice of delta. And now we're ready for the proof of this limit value. So let's see it in action. So generally you start with the following language. Given epsilon bigger than 0, let's take delta to be equal to epsilon over 3. So this is the challenge. Given some arbitrary epsilon bigger than 0, we can find a delta situated in a way that will make everything work out. Okay, and then where do we go from here? So next up, let's notice that after we take this arbitrary epsilon and pick a delta, we have a conditional statement, an if-then statement. So that means we need to prove that using standard rules from proving conditional statements. So we will suppose that x minus a is less than delta and show that that leads to f of x minus L is less than epsilon. Okay, so let's do that. Let's suppose that absolute value of x minus 2 is less than delta, but delta is equal to epsilon over 3. But let's notice that that immediately leads to 3 times the absolute value of x minus 2 is less than epsilon, which immediately leads to the absolute value of 3x minus 6 is less than epsilon, which in turn leads to the absolute value of 3x minus 1 minus 5 is less than epsilon. And that's exactly where we needed to end up. Okay, so now let's do another example. For our next example, we'll show that the limit as x goes to 3 of 2x squared equals 18. So let's take our approach that we did before, starting with our scratch work. So we would like the absolute value of 2x squared minus 18 to be less than epsilon. And recall, we want to root this out until we have an x minus 3 term. So let's try to get there. So we can divide a 2 out of this, giving us 2 times the absolute value of x squared minus 9 is less than epsilon. Then maybe do a couple steps at once. This factors into x minus 3 times x plus 3. I can write both of those in absolute values. And then dividing by 2, we have that's less than epsilon over 2. But now we look at that and we see we have this extra term. And this extra term in this case is this x plus 3 term. So we'd like to somehow take care of that, like maybe bound that above and below by something. Okay, so how can we do that? Well, let's do like a little bit of wishful thinking. So if the absolute value of x minus 3 is less than 1, so in other words, if delta is at least 1 or smaller, which it probably is because we're taking an epsilon to be very small, then we have the following inequality. This will simplify down to -1 is less than x minus 3 is less than 1. That's how compound inequalities arise out of absolute value inequalities. But this is the same thing as what? 2 is less than x, which is less than 4, but we want x plus 3. Notice this means that 5 is less than x plus 3, which is less than, let's see, add 3, we have 7. But now taking the absolute value here doesn't really do anything. Notice this means that the absolute value of x plus 3 is less than 7. Okay, but now plugging this into our inequality that kind of gave us a little bit of pause and then bringing it down leaves us with the absolute value of x minus 3 times 7 is less than epsilon over 2, which means the absolute value of x minus 3 is less than epsilon over 14. So that tells us that should probably be our delta, but notice our delta should also be less than 1 based off of this. So the real problem is how to encode that in our solution. So let's maybe see how we might do that. So let's say we are given an epsilon bigger than 0. Let's take delta to be equal to the minimum of the following two numbers. One number will be 1, and the other number will be epsilon over 14. So you could have a crazy person give you an epsilon of like 20 and then 1 will be smaller. But likely epsilon is super small, like 1 over a million or something. So the 1 doesn't really matter. But that being said, this is the precise way of going about this. Okay, so now where can we go from here? Well, keeping in mind what we did over here, we're going to need a bound for x plus 3. So let's get that bound for x plus 3 first. Now let's see that if we suppose that the absolute value of x minus 3 is less than delta, then that means, first of all, that the absolute value of x minus 3 is less than 1. But then bringing that all out, that tells us that x is between, like we saw over there, 2 and 4. But that means that x plus 3 is between 2 and 7, which means the absolute value of x plus 3 is less than 7. And now with this setup, we're ready to finish it off. So let's maybe put observe or something like that, that the absolute value of 2x squared minus 18 is the same thing as 2 times the absolute value of x minus 3, and then times the absolute value of x plus 3. But now we can put in our inequality right here. And maybe we should change what we have up here to say, notice that x minus 3 is less than 1 and absolute value of x minus 3 is less than epsilon over 14. That's what we get out of this minimum statement, and we'll use each of those. So just to reiterate, we use this less than 1 to derive this inequality for absolute value x plus 3, and we're about to use the epsilon over 14 here. Okay, so now let's use our inequality. So now this is less than 2 times, so we already determined that absolute value of x minus 3 is less than epsilon over 14, so I can put an epsilon over 14 here. And then we know absolute value of x plus 3 is less than 7 from this line here, so times 7 here, but that all turns into epsilon. So in the end, we have absolute value of 2x squared minus 18 is less than epsilon, which was needed. Okay, let's do one more before we prove some standard results involving limits. Okay, so for our last example, before we prove some general results, we'll show that the limit as x goes to 9 of the square root of x equals 3. So again, let's do our scratch work first. Okay, so we will need the absolute value of the square root of x minus 3 to be less than epsilon. And let's look at where we should finish off. Well, we should finish off down here with the absolute value of x minus 9 is less than something. And that something is what we will eventually call delta. So now how can we build absolute value of square root of x minus 3 to absolute value of x minus 9? Well, in this case, we'll want to multiply by something. So what will we multiply by? Well, I think the square root of x plus 3 is a good choice, just based off of difference of squares factorization. And of course, we don't really need this in absolute values because that's always positive, but let's just put them in there to be safe. Okay, so multiplying both sides of this inequality by this term will give us absolute value of x minus 9 on the left-hand side, because square root of x squared is x. And then on the right-hand side, we will have epsilon times the absolute value of the square root of x plus 3. And now we need to bound this square root of x plus 3. And I think we can do that the same way as we did before, but I'm going to need a little bit more room, so let's get rid of this, just keeping in mind that's where we're going. So let's play the game of wishful thinking, and let's say what would happen if the absolute value of x minus 9 was less than 1. Well, that means that x is between 8 and 10. But then if we take the square root of x, we'll see that the square root of x is between the square root of 8 and the square root of 10. But that's a little bit gnarly to work with, so perhaps we'll round each of them to their closest perfect square. So this is less than the square root of 16, which is 4, and this is larger than the square root of 4, which is 2. So deleting out the middle, we have 2 is less than the square root of x, which is less than 4. Now we can add 3 to all parts of this, and we'll see that 5 is less than the square root of x plus 3, which is less than 7. But in this case, since our absolute value of x plus 3 lives in the numerator of the calculation, we're actually going to need to bound it below. So let's take that. We have the absolute value of the square root of x plus 3 is bigger than 5. And that gives us motivation to take delta to be equal to 5 times epsilon, not epsilon over 5. Again, because things are happening in the numerator instead of in the denominator like in the previous case. And now we're ready to write down our final solution. So let's say we are given epsilon bigger than 0. Let's take delta to be equal to the minimum of 1 and 5 times epsilon. And first, we will derive this inequality. First, if the absolute value of x minus 9 is less than delta, then in turn, it's less than or equal to 1, which leads to the absolute value of x plus 3 bigger than 5 by that calculation we did over there. And now we're ready to finish this thing off. So let's maybe write it in a slightly different order just for some variety. So let's maybe say, note the following calculation. We have 5 epsilon is bigger than or equal to delta, since delta is the minimum of these two, but delta is bigger than the absolute value of x minus 9, but that's equal to the absolute value of the square root of x minus 3 times the absolute value of the square root of x plus 3 by factorization. But now that in turn is bigger than 5 times the absolute value of x minus 3 by this inequality right here, which we derived over on the scratch work. But now, I just had my epsilon backwards, but now reading this and dividing by 5, we get exactly what we need. This leads to the absolute value of the square root of x minus 3 is less than epsilon, which is exactly what we need for this limit to have the following value. Okay, so now let's prove some more general results. For our main result, we'll prove standard limit rules that you learned in calculus. So let's suppose the limit as x goes to a of f of x is L, and the limit as x goes to a of g of x is M. So in other words, the two limits exist. Then we will show the following 4 statements hold. So first, the limit as x goes to a of c times f of x is c times L. So where c is a constant multiple. I haven't written that here, but let's assume c is a constant, so a real number. So in other words, we can essentially factor this c out. Then next, we'll show the sum rule. So the limit of the sum of two functions is equal to the sum of the limits. Next, the product rule. So the limit of the product of two functions is equal to the product of the limits. And finally, the quotient rule. The limit of the quotient of two functions is equal to the quotient of the limits. Of course, there, we need that bottom limit is not equal to 0. Okay, so let's get going with this first statement. So let's say we are given epsilon bigger than 0, and we'll first use this epsilon along with the fact that our limit of f of x is L in this case. So let's take delta bigger than 0 such that if absolute value of x minus a is less than delta, then the absolute value of f of x minus L is not less than epsilon, but it's less than epsilon over c. So something like that. And now we're ready to essentially finish this thing off. So let's note that our final goal is the absolute value of c times f of x minus c times L, which we can factor a c out of, giving us f of x minus L. But recall that we built this to be less than epsilon over c, so this is less than c times epsilon over c, which is equal to epsilon. I guess I should state here that c is not just a constant, but it's a non-zero constant for this to work. I'll let you think about the case what happens when c is the 0 constant. Okay, so let's see, did we do it? Yes, given an epsilon bigger than 0, we found a delta out of our original assumption so that this difference here was less than epsilon as needed. Okay, let's move on to our second statement. Now for our second statement. So again, let's say we are given epsilon bigger than 0. Let's take delta 1 and delta 2 bigger than 0 such that if absolute value of x minus a is less than delta 1, then the absolute value of f of x minus L is less than epsilon over 2. Okay, so we can do that because of this limit which was given. And then also, absolute value of x minus a less than delta 2 should imply that the absolute value of g of x minus m is also less than epsilon over 2. Great. And now we're ready to finish this thing off. Well, we have to find our final delta. So let's take delta to be equal to the minimum of delta 1 and delta 2, and note the following calculation finishes it off. So the absolute value of f of x plus g of x minus L plus m by the triangle inequality separates out into the absolute value of f of x minus L plus the absolute value of g of x minus m. So just to reiterate, there we use the triangle inequality after moving some things around here, but we did use the triangle inequality there. But notice now we want to apply this rule up here, but we need to include a statement here, which I forgot. If absolute value of x minus a is less than delta. So if it's less than delta, then it's less than both delta 1 and delta 2, which means that this object right here is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. So that finishes this proof off. Okay, now let's do our product rule proof. Okay, so now for our product rule, which is a bit trickier. So let's see how that goes. So let's say we are given epsilon bigger than 0. Let's take the following 3 deltas. So let's look at these. So our first delta will be chosen as follows. So delta 1 bigger than 0 such that if x minus a is less than delta 1, then, which I'll write as an implication, we have absolute value of g of x minus m is less than 1. Okay, well that may not seem super helpful, but let's see where that leads us. So that'll lead us to m minus 1 is less than g of x, which is less than m plus 1. So that's pretty easy to unravel this absolute value inequality to this compound inequality. But retrieving an absolute value back into this, we'll see that this means the absolute value of g of x is less than the absolute value of m plus 1. Okay, great. So that's how we choose our delta 1 so that this occurs. But the real takeaway here is that we actually chose this delta 1 so that this inequality over here happened. Okay, now we'll choose our delta 2 and our delta 3 a little bit more like we did before. So let's take delta 2 bigger than 0 such that x minus a less than delta 2 in absolute values implies f of x minus l less than not epsilon over 2, but epsilon over 2 times this object. So 2 times absolute value of m plus 1. And now we'll choose delta 3 kind of in concert with this, but with the function g of x. So delta 3 will be chosen such that the absolute value of x minus 3 less than delta 3 implies absolute value of g of x minus m is less than epsilon over 2 times the absolute value of l plus 1 in this case. And notice by our construction, those denominators are never 0, so that's okay. Now, finally, let's set our delta to be equal to the minimum of delta 1, delta 2, and delta 3. And then we're ready to finish this thing off. So if absolute value of x minus a is less than delta, then that means it's less than or equal to delta 1, delta 2, and delta 3. So that's good. And now we can see that in this case, the absolute value of f of x times g of x minus l times m simplifies as follows. So we'll start by adding a version of 0 in there. And that version of 0 will be l times g of x. So this is equal to the absolute value of f of x times g of x minus l times g of x plus l times g of x minus l times m, like that, in absolute values. But now we can see that we've got a common g of x factor here, and we have a common l factor here. And then we can use the triangle inequality to take those into 2 absolute values. So that's going to say that this is less than the absolute value of g of x times, let's see, the absolute value of f of x minus l is going to be left over after pulling that g of x out. And then we'll have plus the absolute value of l after pulling that out, and then times the absolute value of g of x minus m is what's left over after that. But now let's notice that the absolute value of g of x is less than absolute value of m plus l. So that'll cancel this f of x minus l's denominator down to epsilon over 2. And then we'll have an L times epsilon, so plus absolute value of L times epsilon over 2 times absolute value of L plus 1. So that occurs from this last term. But notice that this L plus 1 and this L will cancel that down to epsilon over 2 with the correct inequality, giving us this whole thing is less than epsilon over 2 plus epsilon over 2, which is epsilon. And that finishes this whole thing off. Okay, so now let's do our quotient rule. Now let's work on our quotient rule, the last thing that we need. But we're going to prove a specialized version of this. We'll prove the case when f of x is equal to 1. So we'll prove the limit as x goes to a of 1 over g of x is in fact equal to 1 over m if m is not equal to 0. But that combined with number 2 would give us, but that combined with the product rule would give us exactly what we wanted there. Okay, so let's do that. Well, maybe we'll put a box around this to show that this is actually what we are proving. So let's say we're given epsilon bigger than 0, let's take the following deltas. So let's take delta 1 bigger than 0, that makes the following happen. And that is that if x minus a is less than delta 1, then we have absolute value of g of x minus m is less than the absolute value of m over 2. Okay, so again, that's possible. We're just taking our epsilon to be absolute value of m over 2 in that case. But now let's see where that takes us. So we have the absolute value of g of x minus m is, using one of those triangle inequalities, will be bigger than or equal to the absolute value of m minus the absolute value of g of x. But then this can be pinned on the left by absolute value of m over 2. So now putting those two things together, we'll see that the absolute value of g of x is bigger than the absolute value of m over 2. So again, that's from those two portions right there. But we're going to need something involving 1 over the absolute value of g of x. So let's notice that 1 over the absolute value of g of x is less than 2 over the absolute value of m. But we don't actually need it like this. We need it in one other version, which I'll summarize up here. And that is 1 over absolute value of m times absolute value of g of x is less than 2 over absolute value of m quantity squared. Okay, good. Now I'm going to get rid of this, and then we'll talk about our delta 2 choice and finish this up. Okay, now we're ready to talk about our delta 2 choice. So we'll choose delta 2 bigger than 0 such that x minus a is less than delta 2 implies the following. And you'll see all of this come together. So we'll have absolute value of g of x minus m is less than epsilon times the absolute value of m squared over 2. And that's motivated by this inequality that we built before. Okay, so now we're ready to finish it off. So let's set delta equal to the minimum of these two, delta 1 and delta 2, and observe that if the absolute value of x minus a is less than delta, then the following calculation holds. So the absolute value of 1 over g of x minus 1 over m turns into the absolute value of g of x minus m over m times g of x just by finding a common denominator. But then we can split these absolute values up and see that we get the absolute value of g of x minus m in the numerator over the absolute value of m times the absolute value of g of x in the denominator. But now we can apply our two deltas. So delta 1 will give us this inequality, and delta 2 will give us this inequality. So this is less than 2 times epsilon times absolute value of m squared over 2 times absolute value of m squared when putting it all together, but that's equal to epsilon. And that finishes off this last case. So now I'll leave you with some warm-up. So here are 3 nice warm-up problems based off the precise definition of the limit. So you'll use that precise definition to prove the limit as x goes to 4 of 2x plus 1 is 9, limit as x goes to negative 3 of x squared minus 2 is 7, and finally limit as x goes to 2 of 2x minus 1 over 3x plus 4 is 3 over 10. And that's a good place to stop.